Hello, my name is Bojan Mitov, the president of Mitov Software, and in this session we will cover creating Internet of Things solutions with Delphi and Arduino. What is Arduino from a hardware point of view? It is a low-cost, open-source hardware microcontroller board. It is resilient, very difficult to damage hardware, suitable to be used by non-experienced users. There is a huge number of clones and boards, with new ones appearing every day. It is simple to use hardware design, and it is very good for real-time tasks. What is Arduino from a software point of view? When Arduino was developed, the team also developed a simple integrated development environment and standard API. They made it open, and as new platforms and boards appear, they were made to support the IDE toolchain and the API. And now the Arduino IDE is capable of programming many different non-Arduino based devices such as Tinsy, Edison, Galileo, ESP8266, FreeSOC2, and even Raspberry Pi. Since the API is standardized, it allows very easy code sharing between the different hardware platforms. Here are some examples of Arduino type boards and examples of some of the clones. Why use the Arduino for Internet of Things? It's a very low-cost platform. Some boards as cheap as $2 or less. Most boards have a large number of digital and analog channels. There is a large number of connectivity options over Ethernet, Wi-Fi, Bluetooth, GSM, GPRS, and many others. There is large variety of sizes starting with a small coin size to a palm size boards. There is also a huge amount of available peripherals. What are the challenges of using Arduino? The IDE and the development tools are quite primitive and difficult to learn and use. The required programming is relatively low level and quite challenging. Most people have no problem connecting hardware to it, but they tend to get lost when trying to program it. There is a lack of easily available debugging tools, so most debugging is done through printing messages over serial port. When used for collecting data, there is no easy way to visualize it, especially when working with multiple channels. There are no readily available tools to communicate with it from Delphi or C++ Builder. Because of these challenges, Visuino was developed. Visuino is a graphical development environment for Arduino. It automatically generates Arduino code and programs the boards. It also includes built-in data visualization tools for displaying multiple channels of data arriving from the boards. Visuino has direct mapping of software and hardware components, making the development very easy. It provides uniform communication over serial or socket-based channels. It includes serial port and socket communications components compatible with Communication Lab for Delphi and C++ Builder. Here is how Visuino works. You create your visual design in Visuino. By clicking a single button, it will automatically generate the code and start the Arduino IDE, where you can compile and upload the code to your Arduino devices. Here is how Visuino integrates with the rest of the Mitov software solutions. You can use Visuino to program Arduino with serial or socket communication to send and receive packetized or non-packetized data. In Delphi, C++ Builder, Visual C++, and .NET, you can use Communication Lab from Mitov Software to receive the data from Arduino and send other data back. OpenWire Studio has the same communication capabilities and can integrate with Arduino the same way. In addition, Visuino, Communication Lab, and OpenWire Studio all contain MQTT messaging protocol components, and with the help of MQTT server can communicate with each other. How to communicate with Visuino programmed Arduinos from Delphi and C++ Builder. Communication Lab allows direct communication over serial port or sockets. It can receive or send raw or structured data. It allows a direct integration with the rest of the Mitu software libraries over OpenWire connections. When you start Visuino, in the center will be your design area. Here you have visual representation of the Arduino board with all of its channels. On the left, you have navigation panel, and below it, the properties panel, where you can edit the properties of the selected component. On the right side will be the components toolbar, where the components are organized in categories and subcategories. You can expand all of the categories or collapse them. A component can appear in more than one categories based on its functionality. You can also search for components, and the filtered result will be shown. Below the design area is the serial communication and the scope views. Here you can monitor your communication with the Arduino when connected. Traditionally, the first project to try when programming Arduino is the so-called Blink project. Arduino has built-in LED on pin 13, and we can make the LED to turn on and off with some frequency. To do this in Visuino, we can add a pulse generator with frequency of 1 Hz and connect it to pin 13. If we click on this button, Visuino will generate the Arduino code and will open the Arduino IDE. Here we can select our Arduino board, in my case Arduino Nano, and the port to which the board is connected. If we click on this button, the Arduino IDE will compile and upload the code to the board. You can see that our LED on the controller is blinking. To keep the projects more interesting, we will leave the pulse generator to keep blinking our LED, and we'll add more functionality. I have added a joystick to the Arduino Nano, and the X and Y coordinates from the joystick are sent to the analog pin 0 and 1. The easiest thing we can do is connect analog pin 0 to the serial port, generate the code, compile and upload it to the Arduino. In the serial terminal, we can select COM port where the Arduino is connected and click Connect. We will see the values arriving from Arduino. If I move the joystick, you'll see the values changing. And we can monitor the changes in the scope. Now let's connect to Arduino from Delphi. We'll start with new VCL project, add a COM port component, and a terminal component. We will connect them together, select the COM port to monitor, compile and run the application. And you will see the data arriving from Arduino. This is good, however, our joystick has both X and Y coordinates, and it has a switch when you press the controller down. We would like to see all of those channels. Sending them as text through the serial port is not the most convenient way to monitor them. Visuino includes a packet component that allows you to packet multiple channels together and send them through the serial port. We will drop the component. We will add 2 analog channels and 1 digital channel. We will specify a unique head marker so we can find the beginning of each packet, disconnect the old connection to the serial port, and connect our packet to the serial port. Analog channel 1 to analog channel 0 of Arduino, and analog channel 1 of Arduino to analog channel 2 of the packet component. Finally, digital channel 1 of the packet component to digital pin 2 of the Arduino, where the switch of the joystick is connected. This particular joystick does not have pull-up resistor for the switch, so we will use the built-in pull-up resistor in Arduino for channel 2 by enabling it in the property editor. The project is ready and we can upload it to Arduino. In Visuino, we can select for format of the serial packet 1. The scope will be configured for the 3 channels of the packet 1 component, and visual instrumentation panel will appear showing us the 3 channels. If we connect, you will see that we can control the data with the joystick. It is plotted on the scope, and displayed in the visual instrumentation. Now we will connect from Delphi. We will drop COM port component, unpacket component, scope component, 2 gauges, and an LED. We will switch to the open wire view, connect the COM port to the unpacket, add 2 float channels to the packet, and 1 Boolean channel. Set head marker of 5555, the same as in Visuino. Add 2 more channels to the scope, connect the elements to the 3 channels of the scope, connect the first float channel to angular gauge 1, the second one to angular gauge 2, and the Boolean channel to the LED. Select the COM port, For the gauges, set max value of 1. Compile and run the application. You can see the data arriving from the Arduino and being displayed on the gauges and on the scope. In addition to Arduino, Visuino also supports the ESP8266 microcontroller. It has built-in Wi-Fi. It is low cost, very small, about the size of a coin. It can be powered by 3.3 volt coin battery. It is supported by the Arduino IDE and Visuino, and there are a number of ready-to-use USB-enabled modules with it, including Node MCU and Wemos. For this project, we will use the Node MCU version. We will select the board time as Node MCU ESP-12. If we select the board and expand the modules, we'll see that we have Wi-Fi capability. Next, we'll add one remote access point. We will set the SSID, in my case ASUS, and the password. For simplicity, we will use a fixed IP address. We will enable the config and we will specify the fixed IP address. It should be address available on your network. In my case, 192.168.0.155. We have the module configured to connect to the hotspot. Now it's time to add sockets. We'll add a server socket and we'll set it to port 8080. We'll use the MPU 6050 accelerometer and gyroscope module. This is I2C module, so we'll connect it to the I2C channel. To send the data over the socket, we will pack it into a structure. We'll use the make structure component. We'll add 7 analog channels. We'll connect the accelerometer to the first 3 channels, the gyroscope to the next 3 channels, and finally the module thermometer to the last channel. We'll connect the output of the make structure component to the input of the socket. To reduce the traffic, we can specify how often we'll send the structure. For this, we'll use a clock component. We'll specify a frequency of 10 Hz. Connect the output of the component to the clock of the make structure. This will ensure that we'll be sending 10 structures per second. The project is ready, and now we can generate the Arduino code. We will select the board. In my case, Node MCU version 0.9. The COM port, compile, and upload the code. The upload is ready. Now let's connect to the module from Delphi. We'll add a socket component. Specify the host address and the port. Add split structure and we'll plot on a scope component. We'll add 7 floating point channels to the split structure. Connect the socket to it. Add 7 channels to the scope. and connect those channels to the split structure. If we compile and run the application, we will see the data arriving from the gyroscope and accelerometer. Unfortunately, in virtual machine, the communication doesn't work as well as on a physical machine, so I cannot show you the real rate of data change. I can assure you that it works much better in a physical machine. A relatively new member to the Arduino family is the Arduino 101. It is Intel Curie-based microcontroller with built-in Bluetooth LE, gyroscope, and accelerometer. It is supported both by the Arduino IDE and Visuino, and since it has Bluetooth, it is a good candidate to communicate with it from Delphi program mobile devices. We will start new Visuino project. Select Arduino 101 as board. Expand the modules, Bluetooth, and set a local name. Any relatively short name is a good one. Next, we'll add a Bluetooth service. And we'll connect it to the input of the Bluetooth module on the Arduino. Then we'll add two analog characteristics. We'll send the temperature to the first characteristic, and we will use the second one to control a servo. For this, we need to add a servo component. Our servo will be connected to digital pin 2 and will be controlled by the characteristic. The project is ready, and now we can generate the Arduino code. We will select the board type as Arduino 101 and the COM port. Then compile and upload the code. The code is uploaded. Now let's take a look at the FireMonkey Delphi application that can control our Arduino through Bluetooth. We'll use the standard Delphi Bluetooth LE component. We'll also add a timer, label, and a track bar. We'll set the min and max of the track bar to 0 and 1000. We'll disable the timer, enable the Bluetooth. The first thing we'll need in the code is definitions for the ID of our service, temperature, and servo characteristics. Visuino generates IDs for the service and characteristics automatically when you add new service or characteristic, so we can copy and paste them. I have already done that. The next task is to discover the Bluetooth devices when the form is created. In the on-end Discover Devices event of the Bluetooth component, we will iterate through the devices, force the services to be discovered, check if our service is available. If it is available, this obviously is our device. We'll assign it to a member variable. We'll enable the timer, use this special trick to force the characteristics to be discovered, obtain the temperature and the servo characteristics, and also assign them to member variables for later usage. On timer, we will use a special flag to indicate if we are sending. If we are not, we will read the temperature. In the characteristic read, we'll assign the obtained temperature to the text of the label. If the track bar is changed, we'll set another flag indicating that it is changed. And in our timer event handler, if the track bar was changed, we'll send the new position normalized to the server. And we'll set the sending flag to true and clear the change flag. Finally, in the Bluetooth on characteristic write, we will simply clear the sending flag indicating that we have completed sending the characteristic. Now we can compile and run the application on our device. You can see the temperature displayed here in the label. And if we move the track bar, the servo will follow the movement. We can also use Bluetooth Classic to connect to Arduino from Delphi. For this, on the Arduino side, you can use the HC06 module. It is an easy-to-use, low-cost Bluetooth module for Arduino. It implements serial port Bluetooth service. This makes it very easy to use on the Arduino and Delphi sides. We will use the Bluetooth to remotely control a robot car. I have used the Lego robot car. It's a great low-cost kit manufactured by Lego. You can see their website. For its feature set, this is by far the most affordable robot kit that I have seen so far. It includes HC06 Bluetooth module for remote control, which makes it a great candidate for our demo. It also comes with rechargeable batteries with charging station, infrared remote and receiver, infrared line tracking sensors, and ultrasonic distance sensor mounted on top of servo that allows it to be rotated and measure distances in different directions. Let's start with the robot design in Visuino. To control the motors, the robot contains a motor driver board based on the L298N chip. We need to add Visuino component for it. In this kit, the motor board is connected with 3 pins per motor. We'll add the motor driver, connect the forward to the digital pin of digital channel 7, the reverse to digital channel 6, the speed to the analog pin of digital channel 5. For the second motor, the forward to digital channel 8, reverse to digital channel 9, and speed to the analog pin of digital channel 10. The dual motor driver component has 2 input pins to control the speed of the 2 motors. We'll send sudden values for the motors to go forward, backward, or stop. This will work, however, the motors will turn suddenly, and this will not be a smooth ride for the robot. It is best if we introduce transition between the values with a ramp. Visuino includes special component exactly for this purpose. The ramp to value component. We will add 2 of them. For the 2 motors, and we'll connect them. We will set initial value for the components to 0.5, which means stop for the motor. The speeds for the motors are 0 backward, 0.5 neutral, and 1 forward. For slope, we'll set 1.5. We will control the robot with 4 buttons: forward, backward, left, and right. When none of them is pressed, the robot should not move. This means that we have 5 different conditions. The simplest way to implement this in Visuino is to use array component. We will add 2 analog arrays for the 2 motors. And we will connect them to the ramp components. Now we will add the speeds for the 5 conditions in array 1. 0.5 or stop for neutral, 1 for forward, 1 for left, 0 for right, and 0 for backward. And we will do the same for the second array. 0.5 for neutral, 1 forward, 0 left, 1 right, and 0 backward. To select index in the array, we will use priority encoder to generate value when one of the buttons is pressed. We will connect the priority encoder to the index pins of the arrays. We will receive 4 different characters from the serial port: F for forward, B for backward, L for left, and R for right. We need to detect those characters. We can do this by comparing them with character constant. For this, we use compare component. We will add 4 compare char value components. We will add 3 more pins to the priority encoder. We'll set the 4 characters for the buttons: F for forward, L for left, R for right, B for backward. And we will connect the components to the priority encoder. Now all we need to do is connect the serial port to the compare components. If necessary, you can rearrange around the forward, left, right, and backward commands to match the left and right motors in case your robot is wired slightly different. Since the Bluetooth module is connected to the serial port, make sure you remove the module before programming the robot. The project is ready. Now we can generate the Arduino code. Select board, port, compile, and upload the code. To control the robot from a mobile device, I have created a FireMonkey application in Delphi. I have added Bluetooth component, label to show when the device is connecting, 4 buttons to control the direction. I have set the buttons to be disabled, and I will enable them when we connect. Set the enabled property of the Bluetooth to true when the form is created. we will call discover devices on the Bluetooth. When the discovery ends, we will look through the devices, searching for the HC06 device. If we find it, we will pair with the device. We will look through the services. For the first service, we will create a client socket component. We will connect to the socket, and when the connection is established, we will make the label invisible and enable the buttons. Then we will break the two loops. We will save the socket in a member variable. For the mouse down at the forward button, we will send F through the socket. For mouse up, uppercase left. The same thing for the rest of the buttons. Lowercase L for the left down, uppercase L for the left up, lowercase r for the mouse down of right, uppercase R for the mouse up on the right, lowercase b for mouse down on backward, uppercase B for mouse up on the backward. Finally, when the form is destroyed, we will free and null the socket. This is all the necessary code. In order for the application to be able to use the Bluetooth, in the project options, we need to set the Bluetooth and Bluetooth admin to true. Now we can compile and deploy the app to the phone. Control the robot by pressing the buttons forward, backward, forward again, left, right, left, forward, backward, forward, left, right, forward. To connect Internet of Things devices, you can also use MQTT. It is lightweight messaging protocol. It is supported by a number of servers, including Adafruit IO. It supports subscription and push notifications. Because it is so lightweight, it is quite suitable for IoT devices. It is supported by Visuino and Communication Lab in Delphi. For this project, we will use the Adafruit IO server. It is a free server and it is fairly simple to use with MQTT. Adafruit has tutorial on how to set up your MQTT account and how to create your feeds. I have created 2 feeds as they show in their tutorials, PhotoCell and on-off. I have also created dashboard using those 2 feeds. This is all described in the Adafruit IO tutorials. Please follow them to set up your account. Next, we will create our Visuino project. We will use Arduino Mega for this project with Ethernet Shield installed. Expand shields and Ethernet shield. Set up the MAC address. I will use the MAC address from the online Arduino tutorials, but you can use MAC address generator to generate unique MAC address. We need to add client socket to connect to the Adafruit server. We will set the port to 1883, which is the standard MQTT port, and for host, following the Adafruit IO tutorial, we will set io.adafruit.com. Next, we will add MQTT client. I will set up my username for the MQTT server account. Next, following Datafruit IO tutorial, we need to use Datafruit key as password. We can go to one of the feeds, view the key, copy, and paste it. Next, we will add 2 topics. Again, following Datafruit IO tutorial. The first will be your username feeds on off. The second, your username feeds photocell. Now we will connect the MQTT client to the socket. The output from the socket to the input of the client, the output of the client to the input of the socket, the disconnect from the client to disconnect of the socket, and connect from socket to connect of the client. To send data to MQTT, we will use photocell connected to analog input 0. If we connect it directly to the MQTT client, it will send way too much data, overwhelming the communication. Instead, we'll send data once a second using clock generator. And a snapshot component. The snapshot component will get data from the analog input and send it to topic 2 of our MQTT client. The clock generator will send clock signal once a second to the snapshot. The output of text topic 1 will be connected to the serial port so we can see it in serial terminal. The project is ready. Now we can generate the Arduino code. Select board, COM port, compile and upload the code. The upload is completed. If we connect to Adafruit IO with web browser from desktop or mobile device, we can open our dashboard and we can see that as we move the photocell in different directions, the value will change. And if we cover it, it will drop very low. We can also open serial terminal and when we change the value on the dashboard, the change will be reflected in the serial terminal and on any other connected device to the MQTT. Next, we'll connect to MQTT from Delphi. We will add socket component, set the host and the port, add MQTT component, set the username, and again the Adafruit key as password. To display the topics, we will use 2 label components from UserLab. They can directly receive and display text data. We will add two topics to the client. Both of them read topics, as we will just read for now from the Adafruit.io. Again, we'll set the topic for the first topic and for the second exactly the same way as we did in Visuino. We will connect the output of the socket to the input of the MQTT client and the output of the MQTT client to the input of the client socket. The output of the first text topic to label 1 and the output of the second text topic to label 2. The project is ready. Now we can compile and run it. You can see the data displayed in the project the same way as on the website. And if we move the photoresistor, the value will change. If we cover it, it will drop almost to 0. We can also change the on-off value from the website, and it will be displayed in our Delphi application. We can also add write and read-write topics to the MQTT client and send data from Delphi to the server and to other subscribed devices or Delphi applications. I will leave you to experiment on your own. This concludes our session. My name again is Bojan Mitov, the president of Mitov Software. Mitov Software has a number of products for video processing, audio processing, digital signal processing, computer vision, data visualization, visual instrumentation, artificial intelligence, Boolean logic, universal animations, serial and TCP communication, visual live binding library, and a free advanced runtime library. We also developed the OpenWire Studio, a graphical development environment for Windows, and Visuino, a graphical development environment for Arduino. Mitov Software also supports the OpenWire open source library and the IGDI Plus open source library. Thank you for listening, and now it's time for questions and answers.